Hi everyone, this is Rose, and this is a video about recombination that I made for the summary lecture. So fun thing is that I just recorded this entire thing, but I turned off my microphone, so now I have to redo it, which I love in the evening. Let's get started. Okay, so to explain recombination to you, I will use this example with 4 loci on 2 different chromosomes. So on the left we have a chromosome with 3 loci, A, B, and C, and on the right a chromosome with 1 locus, D. And these are chromosomes of a fruit fly, and we have 4 different phenotypes. 1 curly wings, purple eyes, long legs, and many bristles. So the first example I'm going to quickly explain is independent segregation. So that is what we see, for example, when 2 loci are located on 2 different chromosomes, but also if 2 chromosomes are located on the same chromosome, but when they're really far apart. And in that case, the loci are independent, and that means that there is no linkage. And in these cases, we see what we've seen in Mendelian genetics. So what we see is, for example, if we have 2 parents which are homozygotes, like they're two true breeding lines. On the left, they're homozygote for the dominant alleles. On the right, they're homozygote for the recessive alleles. It means that for both the parents, the gametes, 100% of the gametes on the left will be big A, big D, and 100% of the gametes on the right will be small a, small d. And that means that F1 will be identical and they will all be heterozygote for both loci. And then when we take this F1 and we perform a test cross, meaning we cross the F1 with individuals that are homozygote for the recessive allele, then what we get is this. 100% of the gametes for the right individual are going to be small a, small d, but on the left, we'll see that 50% receives a big A, 50% receives a small a, and then for the D locus, 50% receives a big D, and 50% receives a small d, and this happens randomly. So that means because it happens randomly, they're independent. That means that 25% will be big A, big D, 25% big A, small d, etc., etc. These gametes together in our offspring in the F2, we'll see this 1 to 1 to 1 to 1 ratio of phenotypes. And that is because the loci are independent, and that means there is no linkage. That's why we see this. For example, now we took locus A and locus D. If we would have gone for locus B and locus D, or locus C and locus D, we would have seen exactly the same distribution. So now let's go to the interesting part, the 3 loci A, B, and C, which are located on the same chromosome. Because they're located on the same chromosome and they're located quite closely to each other, it means that the loci are dependent, and that means that they are linked. Okay, so we start off with 2 parent lines. On the left, we have a parent line that is completely homozygote for the dominant alleles for all 3 loci. And on the right, we have a line that is completely homozygote for the recessive alleles of the 3 loci. And then we cross them, and what do we get? Oh, we get a text box saying that this is how you write the genotype when you're talking about linkage. So that means that 1/2 of this genotype is one chromosome and the other half is the other chromosome. And we'll see that right here. And the next slide. First, we talk about the gametes. So for the left individual, 100% of the gametes will be big A, big B, big C. And on the right, 100% of the gametes will be small a, small b, small c. Gametes, we get the F1, and there we see, here we see it. This chromosome here, it received it from the right parent, and here on the right part, it received it from the right parent. The phenotype will be, they're completely heterozygote for all the loci, so that means that it will have the wild type phenotype it will have the wild type phenotype for all the 3 traits. Okay, so now let's do a test cross for the F1. So up here we have the F1 individuals, completely heterozygote, and we're crossing it with a completely homozygote for all three loci. And that means again for the right individual, all the gametes will be small a, small b, small c. On the left, it's gonna be interesting. Woohoo! Okay, so here we have our F1 individual, heterozygote for all loci. And then comes meiosis. So first of all, the DNA has to duplicate. And then two homologous chromosomes get very close to each other. And that's when they start to mingle. And once they have mingled and they're separated, we get this beautiful product, which is 8 different gametes. Okay, so here we have our 8 gametes. And the top 2 are known as the parentals. And that is because in these gametes, the chromosome is identical to one of the parents' chromosomes. Then we have the single crossovers, which are the first single crossovers, which are single crossover between A and B. And then we have single crossovers 2, which are a single crossover between B and C. And then we have the double crossovers, which are crossovers that have gametes in which there was both a single crossover between A and B and a crossover between B and C. So that's not a single crossover between A and B. It's just a crossover between A and B, a crossover between B and C. So how do we identify these 4 categories of gametes? Well, it's very simple. The parents are the ones with the highest frequency. The double crossovers are the ones with the lowest frequencies, and the single crossovers are just somewhere in between. So here again, we're back to the overview. We have our F1 that we cross with a completely homozygote parent for the recessive alleles. So we have parent 1 on the left, parent 2 on the right. And then we see that parent 1 has 8 possible gametes and parent 2 has only 1 gamete. To a more schematic overview. Here we have the gametes for parent 1, which are 8 different ones. Then we have the gametes. Oh, wow, it's late. The gametes of parent 2, which are always going to be small a, small b, small c. And then when we have the genotype for the F2, it's just a blend of these 2 gametes. And that means what we now see very nicely is that because it always has those 3 recessive alleles from parent 2, it doesn't really matter what we see there. So when we look at the phenotype, we see that the phenotype of the F2 is actually identical to the gametes of parent 1. So if the parent 1 gave a gamete big A, big B, big C, the phenotype will be dominant for all the traits. So what we know now is that when we do a test cross, the phenotype of the offspring reveals the gamete of parent 1. So how do we use these phenotypes? We use the F2 phenotype frequencies to tell the following things. I shouldn't click while I do animation. The linkage between the linkage genotype of the parents. We can tell this from the F2 phenotypes, the order of the loci, and the distance between the loci. So I'm going to use an example to calculate, to show you a calculation. And this will be an assignment you made in week 3 of the course. And it was the first to, so it was the one on Tuesday or Wednesday. Okay, so I'm going to be telling you in steps. Here in the right corner is going to say the step. Step 1, put them into order. Make your life easy. Put them into order. Why is that nice? It's nice for step 2. Step 2, define the parentals, the single crossovers, and the double crossovers. So the parentals are the ones with the highest frequencies, so that's the top 2 ones. Woohoo! And then the double crossovers are the ones with the lowest frequencies, the bottom 2 ones. And single crossovers are anything in between. And now we know the parentals. We also know what the parent must have looked like, which was one of the questions. So the parent must have looked like Z plus F and plus VF. So its genotype must have been Z plus F and plus VF plus V plus. The other parent must have been it was homozygote for all the recessive alleles because it was a test cross that was done. Okay, step 3, define the order of the loci. So what we do is, to do this, we only look at the parentals and the double crossovers. And before we start, you should know that the order that you see here, in this case we have ZVF, this order is completely random. It could have been anything. It could have been FZV, or it could have been FVZ, or ZFV. It really could have been anything. We picked ZVF. And now we have to decide what the real order is. So how do we do this? We check which two alleles are the same for the parentals and the double crossovers. What do I mean by that? I mean this. For both the parents and the double crossovers, we see that the Z and the plus are together and the plus and the V are together. And that means that F is in the middle. So now we know that if F is in the middle, Z and V are on the sides. So the order is ZFV. If it can also be VFZ, if that feels nicer to you. Both correct. Potato, potato. So let me see. I was going to say something else. Oh yeah. This is my way of deciding which of the loci is in the middle. You can choose another way. There are several ways that are described in the book. Just pick the one that fits for your brain. Let's see. Yes. So what I always do is I double check if the order that I picked made sense. So I'm just going to do a test run. Okay. From the previous assignment, from the previous step, we knew that the parent's genotype must have been ZF plus and plus plus V, which came from the parentals here up here. So then, if this is the case, its genotype its chromosomes must have looked like this: ZF plus and plus plus V. That means when a double crossover occurred between Z and F, a crossover occurred between F and V. And that means that the two gametes that would come out of this would be Z plus plus and plus FV. I was making noise, but you can't hear it when I make animation. What do we see? We see plus VF, plus FV. It's not the same order, but it's the same thing. Plus FV, plus FV, and then Z plus plus, Z plus plus. Yes, it's correct. Step 4. Calculate the distances between the loci. What is a distance? I get this question quite often, and I also see a lot of confusion in your work. So what is the distance in words? The crossover rate between the two loci. Or the recombination rate between the two loci. Or the percentage of the time that we see a crossover between two loci. Percentage, that means we fractions. So I calculated the fractions here. You simply calculate it by taking the count and you divide it by the total. So 195 divided by 723, it's apparently 0.269. Okay, from the previous step, we know that the order is ZFV. So let's see, how do we calculate the distance between Z and F? We take the single crossovers between Z and F and plus the double crossovers. For the distance between F and V, we take the single crossovers between F and V plus the double crossovers. And the distance between the two extremes, so between Z and V, that is simply the sum of the distance between Z and F and V. And then I get the question, but how do we figure out which one of the single crossovers represent the single crossovers between Z and F, and which ones represent the single crossovers between F and V? So let's start by calculating the distance between Z and F. So what we do, we look at the single crossovers between Z and F, and we look at the double crossovers. And I'll show you why. So the parentals, for the Z and F locus, we see that the Z and F allele are together and the plus and plus allele are together. So that means that when we have a crossover, we would see that the Z and plus are together and the plus and F are together. Now, what I always do for myself is that I cover all the loci that I'm not looking at, and I only look at the two loci that, I'm trying to calculate the distance between. So in this case, that's Z and F. And now what we do, here we see that for these single crossovers, we see that it's Z and plus and F. So these are the single crossovers that we should take into account when we calculate the distance between Z and F. But also, when you look at the double crossovers, you can now nicely see that there is a crossover between Z and F. And then when we calculate the distance, we just sum up the fractions of these crossover classes, and that's it. 16.2 centimorgan. That's the distance between locus Z and locus F. And we can do the same for the loci F and V. So the distance between F and V is the single crossovers between F and V and plus the double crossovers. And here again, we cover up all the loci that we're not looking at. So we're only looking at F and V. And what we then see is that in the parentals, we see that the plus and the F alleles are together, or the V and the plus alleles. And that means automatically that if there is a crossover, that would mean that we would see V and F together or plus and plus together. And then when we look at the single crossovers, we see that it's these two single crossovers that match the criteria. So we see plus plus and VF. And again, when we look down at the double crossovers, we also see this VF and plus plus. So what does this tell us? This is why we're taking the double crossovers into account, because there is a crossover between V and F. And then the final calculation, we just sum up all the fractions of the single crossovers 1 and the double crossovers, and then we get to 33.2 centimorgan. And then the final distance, the distance between Z and V. To calculate the distance between Z and V, we simply take the sum of all the distances that we just calculated. That would give us 16.2 plus 33.2 is 49.4 centimorgan. There is also a different way to do it, and that would be by writing out the equations for the distance between Z and F and the distance between F and V. And in that way, you would get all the single crossovers plus 2 times the double crossovers, and that would give you the distance between Z and V. And if you would do that, you would also find 49.4. And why do we do 2 times the double crossovers? Well, that is because the distance tells us the percentage of the time that we see crossing overs. And a double crossover has 2 crossovers, and that's why we do this 2 times double crossovers. Okay, so let's go back to the question. And I also highly advise you to do this at any exam. Always go back to the question before you write down your final answer. Okay, so they asked, determine the parental genotype, including gamete phase. Talk about this genotype, this linkage genotype. So what you show here is basically you show the 2 gametes that the individual got from its parent. And in this case, the parent got ZF plus, and it got a plus plus V. And then they ask the order of the 3 loci, and we determined that F was in the middle and that Z and V are in the extremes. And then determine the distance between the 3 loci. We found 16.2 centimorgan between Z and F, 33.2 centimorgan between F and V, and by summing them up, we found 49.4 centimorgan between Z and V. Just for a reminder, this 33.2, what does it mean? It means that between F and V, we see recombination 33.2% of the time. And the higher this number, the more recombination and the longer the distance. So if two loci are located very, very, very close to each other, you're going to see less recombination. Okay, this is the end of the video. I hope you understood it, and if you have questions, please let me know.